Let us go over Chemistry 1010 2022 Trial Sheet 1 with the University of Zambia. First question. Which data set has the best combination of accuracy and precision if the true value is 6.72 grams? Now, we know that accuracy is how close measured values are to the true values. So actually it has to do with the comparison between what you have measured and the true value. So if they are close, then you are accurate. Now precision has to do with repeated measurements. Are they close to each other? So if the repeated measurements are close to each other, then such a measurement is precise. So we can start by looking at the first one, 6.71, 6.75, 6.70. Now we can see this, the number which is at the end. We have got 1, we have got 5, we have got 0. Since all of them they are the same, this is too much. Like these values, they differ very much. So wouldn't say this one is, of course, if we consider this value, which is the first decimal point, then this one is going to be what? Is going to be accurate. What do you mean by accurate? Because all these values are not so much away from 6.72, right? And well, they are all 6.7, 6.7, 6.7. What is only differing is the last value. So meaning that they are also close to each other. So we can see that this one is accurate and precise. If we look at B, 6.50, 6.48, 6.52, these values, of course, we can say they are precise because they are all approximately equal to 6.50. So if I round off this one, I'm also get 6.50, also this one. So basically they are precise, but they are not accurate because 6.5, which is the average, it can be the average of this, is so much far away from 6.72, so it is not accurate, right? If we get to look at C, 6.41, 6.72, these values are too far away from each other, so we are not precise. This is imprecise or unprecise, and also not accurate because these values are not close to the measured values. If you want to determine accuracy, because you have got three values here, you have to add them and then you divide by 3 since there are the three of them. So the answer that we are going to get will not be close to 6.72. I can try that. 6.41 plus 6.72 plus 6.55, and then we divide that by 3. That is 6.56, which is very far away from 6.72. And then D, 6.56, 6.7. So you can see 0.5, 0.7, 0.8. These are not precise, neither are they accurate because they're not close to 6.72 if you added them and then divided by 3. So the answer is A. Question 2. How many significant figures are there in the value 8? This was supposed to be, okay, just 8. We have got a decimal point there, times 10 to the power 8. 8 times 10 to the power 8. Now, what can we say? How many significant figures are in this number? Well, if we get to look at this number, 8 point times 10 to the power 8. If we wanted to write this number, well, if we multiply 8 by 10 to the power 8, this is going to give us about 8 with 8 zeros. Okay, something like this. So for this number, you only have one significant figure because these zeros which are this side, they are not significant, right? They are not significant. So that is why it is only one significant figure. Correct formula of iron 3 oxide is, now we've been given iron 3, meaning that it has got a valence of 3. And then we're adding oxygen. Oxygen, you know, it has got a valence of 2 because it's in group 6. It needs 2 electrons to be stable. So these numbers are going to swap. This one comes down and then the 3 also goes down there. So then the formula for iron 3 oxide is going to be written like that. So which one is that? So which is B, right? Question 4. Reagent that can be weighed easily and its mass truly represents the number of moles of substance contained is called. Reagent that can be weighed easily and its mass truly represents the number of moles of substance contained is called. So we have got a standard solution, we have got limiting reagent, we have got primary standard, oxidizing agent. Well, we need to know all these here for us to be able to find the answer for this one. So what can we say? What is a standard solution? That is the first thing that we can ask. So a standard solution is a solution whose concentration is accurately known and also the volume is known. That is a standard solution, right? And then a limiting reagent is the reagent that is used up first in a chemical reaction. When you talk about a primary standard, this is more like a standard solution, but for a primary standard, well, this one you get to use primary standards to be able to standardize other solutions. In other words, it is more like a standard solution. You also know the concentration. Now, it might not necessarily be the concentration, but you also know really its smaller mass, right? You also know the number of moles for this compound. So when you get to react a primary standard with another reactant, you are going to be able to know the mass of this reactant that you've reacted with the primary standard. Because for the primary standard, the number of moles are known and also you have weighed it accurately, right? Now, an oxidizing agent is an agent that oxidizes other substances while it gets reduced in the process. So the answer here then is going to be primary standard. Find the oxidation state of iodine in iodic acid. So we know that the oxidation state for hydrogen is positive 1, plus we want to find the oxidation state for iodine, let me say X, and then we have got 3 oxygens and 1 oxygen, the oxidation state is negative 2. This should give us the total charge. Now we can see that this compound is not charged, so net charge is going to be 0. So it's going to be positive 1 plus X minus 6 is equal to 0. Positive 1 minus 6, that is negative 5. Taking the 5 the other side, that gives us positive 5. So then that is C. Convert 9.3 meters to micrometers. So we have got 9.3 meters. What I'm going to do is I'm going to multiply. Since I've got a meter on top here, I'm going to take this meter down. Then I'm going to have micrometer on top. Now a meter and a micrometer, which one is bigger? We know a meter is bigger. And micro means 10 to the power negative 6. Now because I had put 1 in front of the meter, I had put 1 in front of the bigger unit, then I'm going to say in 1 meter we have got 10 to the power 6 micrometers. Right. So in 1 meter I've got 10 to the power 6 micrometers. That means that 1 micrometer is 10 to the power negative 6 meters. So the meter here will cancel with the meter here. That means that the answer is going to be 9.3 times 10 to the power positive 6 micrometers. So that gives us C. Question number 7. The manufacture of sulfuric acid by the contact process can be represented as follows. We have got sulfur that goes to sulfur dioxide, sulfur trioxide, and then sulfuric acid. Correct sequence of oxidation number of sulfur at each stage is. So I want to write the correct oxidation number. So if we get to look at the first stage, let me just write this down. We have got sulfur into sulfur dioxide, sulfur trioxide, then sulfuric acid. So oxygen here, the sulfur first, is not in any compound, so this is just an element in its form. So the oxidation number of an element is always 0. So this one is 0. And then if we go to the next stage, oxygen, you know the oxidation number is negative 2. But you also have a 2 here. So the oxidation number for sulfur, plus we have got two oxygens, and each oxygen oxidation number is -2. Should give us 0, which is the charge, because this compound is not charged. So sulfur, then the oxidation number is going to be 2 times -2, that's -4. We take it the other side, that is going to be +4. If we go to the other one, which is sulfur trioxide, the oxidation number of sulfur, plus we've got 3 oxygens, each with a -2 charge, should give us 0 because it's not charged. So the oxidation number for sulfur is going to be +6. Now if we go into sulfuric acid, we have got 2 hydrogens, and we know that each hydrogen, the oxidation number is +1. And then we have got a sulfur, plus we have got 4 oxygen, each oxygen, the oxidation number is -2. They should give us 0 because this compound is not charged. So this is going to be +2 plus sulfur minus 8 is equal to 0. And the sulfur, the oxidation number is going to be 2 minus 8, that's -6. Taking the other side is going to give us +6. So then the answer is coming from 0, +4, +6, +6. So which one is that? 0, +4, +6, +6. That is part A, or option A. Question number 8. In which of the following changes is the nitrogen reduced? So the first one, we have got NH3 going to NO. So we need to find the oxidation numbers to determine if nitrogen is reduced or not. Oxygen, of course, we know that the oxidation number is -2. If we add the oxidation number for nitrogen and oxygen, it's supposed to get a 0 because this compound is not charged, meaning that the oxidation number for nitrogen is going to be +2. If we add +2 and -2, we get 0. We know that hydrogen, the oxidation number is +1. So I've got nitrogen plus, I've got 3 hydrogen, and each hydrogen is +1. They should give us 0. So nitrogen, then the oxidation number is going to be -3. So from what we are able to see, nitrogen oxidation number is moving from -3 to +2. So if I find the change in oxidation number, that's the change in oxidation number. Oxidation number on the product is 2. Change is always final minus initial. So minus the initial oxidation number is -3. So this is going to give us +5, meaning that 5 electrons have been transferred. Now because something is coming from being negative to being more positive, something becomes more positive, that is oxidation. Every time something becomes positive, that's oxidation, and oxidation is a loss. So 5 electrons have been lost, right? So this is oxidation. So we want to is reduced, so this is not reduction, so part A will not be the answer. Let's consider the second one. So same here, this is going to be -3, and then we found also the oxidation number for nitrogen in this compound. So nitrogen plus, we have got 3 oxygens, and each has got a charge of -3, should give us the net charge of the compound, which is -1. So this is -6. If we take there, it becomes +6. +6 minus 1 to be +5. So if we look at this compound also, something is becoming more positive, from negative to positive, meaning that this is also oxidation every time something becomes positive. So B won't also be the answer. If we consider 2, we have got nitrogen going into ammonia. We know that in ammonia the charge of nitrogen is -3. Now here, this is a molecule. A molecule, the oxidation number is 0. So I'm moving from 0 to negative. Whenever something becomes more negative, that is reduction. So here nitrogen is being reduced. If we consider the next one, the oxidation number for nitrogen here is 0, but here is -1. So coming from negative to 0, 0 is more positive than a negative. So meaning that this is oxidation. So the answer then is C. Question number 9. Name the reaction given below. We have got potassium dichromate reacted with barium nitrate, and this is going into barium dichromate plus 2 potassium nitrate Okay, here is the reaction. So what kind of reaction is this? So we can see we have formed a solid here. We also have this in aqueous. This is also in aqueous. This is also in aqueous. So when you get to react two salts, so this salt and this salt, and then you get to produce again two salts, such a reaction is a precipitation reaction. Now when you are forming salt, you are going to react two soluble salts or two salts which dissolve. That's why we are able to see aqueous, because these two salts dissolve. And then we are going to produce, every time you react two salts which dissolve, and mostly you are going to form one salt which doesn't dissolve and then the other salt which does dissolve. So this reaction is a precipitation reaction or a double displacement reaction. We can see that the barium are swapped with the potassium. The potassium went to this one, and then the barium came to this one, and hence we found barium dichromate and potassium nitrate. This is a double displacement reaction, which is also a precipitation reaction because we are forming a precipitate or a solid. Right. On complete combustion, 0.246 grams of an organic compound gives 0.198 grams of carbon dioxide, 0.1014 grams of water. What is the ratio of carbon and hydrogen atoms in the compound? So what we have is this organic compound, let me call it X. And we've been told on complete combustion. Now, complete combustion is simply reacting something in oxygen or burning something in oxygen. What you always form is carbon dioxide and water in complete combustion. So if this was incomplete combustion, we would have formed carbon monoxide and water. Right. So what we were burning, we had 0.246 grams and we got 0.198 grams of carbon dioxide and also 0.1014 grams of water. So we want to find out the ratio of carbon and hydrogen in this compound. Now, since we've just been told that this is an organic compound, you know that an organic compound contains carbon, hydrogen. Now, this is not an hydrocarbon, it is an organic compound. It can also contain oxygen, sulfur, phosphorus, those other compounds. So that is why we cannot necessarily say that this compound only contains carbon and hydrogen, because we've not been told if it is an hydrocarbon. They've just said it is an organic compound. Right. So from here, from what we know is that the law of conservation of mass or matter will not be formed nor destroyed but just converted. So the same mass of carbon which was in this compound is the same mass of carbon that we have seen on this side, and the same mass of hydrogen which was in this compound is the same mass of hydrogen that we have seen this side also. So if I find the mass of carbon and hydrogen which are on the product, then that's the mass of carbon and hydrogen which was on the reactant side. Okay. So let's start with first determining the number of moles of carbon. Now we can see that in this compound here, the number of moles of carbon, we can see that for one carbon, we have got one carbon dioxide. Right? For one carbon dioxide, we have got one carbon. So that means that number of moles of carbon is equal to number of moles of carbon dioxide. And how do you get to determine the number of moles of carbon dioxide? That is given by mass over molar mass. The mass of carbon dioxide given is 0.198. The mass of carbon dioxide, we need first to determine the molar mass. Carbon first, the molar mass is 12.0107. And we are going to add, we have got two oxygens. And each oxygen, the mass is 15.9994. So that is going to give us a molar mass of 45.0095. And then we simply divide 0.198 divided by 45.0095. This is going to give us, that gives us 0.004399071 moles of carbon, which are also moles of carbon dioxide. Right. So we have found the number of moles of carbon. Let's also determine the number of moles of hydrogen, okay, which is on the product side. Now, the only hydrogen we can see is in the water molecule. Now we can see that for one water molecule, how many hydrogens do we have? We have got two hydrogens for one water molecule. So what we are going to say is that for each number of moles of hydrogen is equal to 2 number of moles of water. Okay, so number of moles of hydrogen is equal to 2 times the number of moles of water. What do we mean by that? When we are determining the number of moles, actually what we say is number of moles, I'm going to say number of moles of hydrogen is equal to number of moles of water, but we are going to divide by how many there are. So number of moles of hydrogen, we've got 2 hydrogen, so I'm going to divide by 2. So number of moles of hydrogen over 2 is going to be equal to number of moles of water over, we have got one water molecule which gives us 2 hydrogen, so I'll say over 1. So then it is from here that we cross multiply to get a 2, which I put here in front. Okay, so meaning that number of moles of hydrogen is twice the number of moles of water. If you have got 2 moles of water, meaning that you are going to have 4 moles of hydrogen, because you have got 2 hydrogens in one water molecule. So that is the sense that we need to be able to get from here. So I'm going to say 2, but how do you find the number of moles of water? Is mass over molar mass. And this is going to give us 2 the mass of water, that is 0.1014 over molar mass of water. First we get the molar mass of, we have got 2 hydrogens, and each hydrogen, the molar mass is 1.00794, and then we have got one oxygen which is 15.9994. so the molar mass we are going to get is 18.01528, and then we are going to say 0.1014 divided by what is in the denominator, which is 18.01528, and then we get to multiply the answer by 2. So we are going to get 0.011257111. So these are the moles of hydrogen on the product side. So the moles of hydrogen on the product side and the moles of carbon on the product side is what we have determined. So now if we wanted to find if this compound contains any other element, we should convert these moles to mass, these moles to mass. How do you convert? Mass is equal to number of moles times molar mass. So simply multiply by the molar mass of carbon by the molar mass of hydrogen. Would have found the mass of hydrogen and the mass of carbon, and then we get to add those two values, and then the sum we remove from this. What is going to remain will be the mass of other elements which are present in this organic compound. So we just want the ratio of carbon and hydrogen atoms. The ratio of carbon and hydrogen atoms. Now how are we able to determine that? Well, to be able to find that, since we want the ratio of carbon to hydrogen, we'll just get the moles of carbon, which is 0.004399071, to the moles of hydrogen, which is 0.011257111. And then we consider which one is smaller than the other. So from what we are able to see, this is 0.00 and this is just 0.0, meaning that this is bigger than this. Alright, so I'm going to divide both sides by the smaller number. So I'm going to divide this side by 0.004399071. Also this side divide by 0.004399071. Okay, So of course, if we divide something by itself, that is going to give us a 1. And then let's divide also the other side. So that is going to be 0.011257111 divided by 0.004399071. That is going to give us 2.558974527. So I would have rounded off this one to say 2.3. I mean, rounding off, you round off to the nearest one number. So I would have said this 1, 2, 3. Now, when we have something that ends in 0.5, like 2.55, so I'm going to take that these fives are repeating like that, right? And then we know from our mathematics, a rational number 2.55 repeat is a rational number. So I can convert, actually I can just say this is 2.5, only 1 5 like that, since I've got the 2.55 repeating. Okay, this is our rational number. I can express it or convert it in form of a decimal, I mean in form of a fraction. So 2.5 is equal to x, multiply both sides by 10, so we're going to have 10x is equal to 25. And then to remain with x, divide both sides by 10, 25 over 10. So x is going to give us what? 5 into 25 is 5, 5 into 10 is a 2. So actually this is 1 to 5 over 2. Now this is a fraction 5 over 2. So what I'm going to do is I'm going to multiply both sides by what is in the denominator, which is a 2. So 2 times 1, that is going to be 2. Then 2 times 5 over 2, that is going to be 5. So the ratio of carbon to hydrogen in this compound is 2 to 5. So in cases where we've got something ending 2.5, we shouldn't get to round off. We say we write it to the nearest one number, which is a 3. We shouldn't do that. So we get to express that as a fraction, and then what is in the denominator multiply throughout. Question 11. A 35.3 grams of element M is reacted with nitrogen to produce 43.5 grams of compound M3N2. So what we have is M is reacted with nitrogen to produce M3N2. Now we know that the only way you can form such a formula, of course, we should have M reacting with the nitrogen. Now this 2, which is down nitrogen, we don't consider it when you are getting to form this formula. It's just that nitrogen always exists as a diatomic gas. That is why you always include this one, just like oxygen, fluorine, and also hydrogen. Nitrogen is in group 5, meaning that it has got a valence of 3. So the only way this 3 can come from here and come here, where would these 2 come from? It means this 2 has come from here, meaning that this one has got a valence of 2. Okay, it has got a valence of 2. That is why it went down here, and then this one came down here. So that is one thing that we can deduce from here. Now, since we've just been told an element M, we don't know if it is a metal or a non-metal. If it is a non-metal, I would have put a 2 also there, but I don't know if it's a non-metal. So all I'm going to do is to balance this reaction. So I've got a 3M, so I'm going to put a 3 here, right? So now from here we've been told a 35.3 grams of M. So the mass of this one has been given as 35.3 grams. It's reacted to with nitrogen to produce. So what we have produced is 43.5 grams of this compound. So what is the molar mass of the element M? So I want the molar mass of this element M. Now looking at the product side, the only way we can produce this one is the number of moles of this same M divided by the coefficient, which is the 3, should be equal to the number of moles of the product, which is M3N2, divided by the coefficient. What's the coefficient? That is 1. How do you find the number of moles of a compound? Number of moles is given by mass over molar mass, but we already have the 3 down, so that will be 3 molar mass. This is for the compound M. This is going to be equal to mass divided by molar mass. We only have the 1, so I'll not put anything, of the compound M3N2. So the mass of M, that is 35.3 divided by 3, the molar mass of M we don't know. That is going to be equal to the mass of M3N2 which was produced, that is 43.5, divided by the molar mass. Now the molar mass of this compound, let's determine that. So I've got M3N2. So I've got two nitrogens, and then molar mass of nitrogen, checking from the periodic table, it is 14.00672. And then we have got also the molar mass of this compound. So 3, we don't know its molar mass, I'll just say like that. So let's get to multiply 2 multiplied by 14.00672. That is going to give us here as 28.01344. So the molar mass of this compound is the sum of this value and this value which is here. So I'm going to say 28.01344 plus 3 molar mass. This molar mass I'm writing is the molar mass of M, and that is what we want to find. So from here I can do a cross multiplication. So I can multiply 35 by this value, 28.01344 multiplied by 35.3. That is going to give us 63.31344. And then the same 35.3 multiplied by now 3 molar mass. So let's do that. 35.3 multiplied by 3 molar mass, that is going to be 105.9 molar mass. And that is going to be equal to, we get also to multiply this value by that. That is 43.5 multiplied by 3. So that is also going to give us 130.5 molar mass. We'll take like terms to the same side. So I'm going to take this value this side. It's going to be negative. So what you're going to have is 130.5 minus 105.9. That is going to be 63.31344 is equal to 24.6 molar mass. So to remain with the molar mass of M, we'll just divide both sides by 24.6. 63.3144 divided by 24.6. That gets to give me 2.573. Okay, so that is the value that I'm getting for this one. Let me just punch this again. Perhaps I might have done something else because the molar mass is too small for this compound. I'm going to pick it from here. Okay, so we are saying the mass of M, which is 35.3 divided by 3, the molar mass of M, this should be equal to the mass of the product, which is 43.5 divided by the molar mass of this compound. So let me just put X here before I can get to substitute the value that I found earlier. Okay, so from here I'm going to do a cross multiplication. So that is going to give us 35.3 times X. That will be 35.3X, and that is going to be 3 multiplied by 43.5. That is going to be 130.5 with a molar mass. Now we know that this X is representing the molar mass of this compound, since that is the one which is in the denominator. So the molar mass of that compound is going to be a sum of the molar mass of nitrogen, which is 14.00672. Let me check that again on the periodic table. 674. We are multiplying that by 2, and that is 35.5.3 multiplied by the molar mass, which is X, is going to be 28.01348 plus, in this compound we have got a 3m. So we're going to multiply 3 by the molar mass of m, which we don't know. And this is going to be equal to 130.5, the molar mass. So I'm going to divide both sides by 35.3. If you want, you can distribute the 35.3. So it's give me 28.01348 plus the 3 molar mass, and that is equal to, let's get to find that side, 130.5 divided by 35.3. This is the 3.696 molar mass. I'm going to take this 3 also the other side. So it's going to be 3.693 minus 3. So we are going to have 28.01348 being equal to 0.69688 molar mass. And then to remain with the molar mass, we divide the 28.01348 by 0.69, and that is going to give us 40.198. Molar mass is given in grams per mole, so the other value I found was because of wrong punching on the calculator. So this is the molar mass. And then next question is saying name the element m. So we want an element which has got a charge of what? Which has got a charge of positive 2. And it has got a molar mass of 40.198. So just get to check on the periodic table. Charge of 2, that should be in group 2. And it has got a molar mass of 40.1. So if you get to look at calcium, calcium has got a molar mass of 40.07, which is 40.1. So that means that this compound is calcium. Right. Question number 12. In an experiment, 1.90 grams of ammonia reacts with 4.96 grams of oxygen, as you are able to see. Which is a limiting reactant? Show your working. Now, from what you've been given, we have got 4 moles of ammonia reacting with 5 moles of oxygen to produce 4 moles of nitrogen monoxide and also 6 molecules of water. Again, what you've been given, the mass of ammonia is 1.90 grams. The mass of oxygen is 4.96 grams. Right. So what we are going to do is, there are several ways in which we are able to answer this question. I can take, let me say I don't know the mass of this compound, ammonia, which is supposed to react with the oxygen. So let's say I don't know that this is the mass that is supposed to react with the oxygen. So that is one way I can take. So I'm going to remove this. We know that the mass given is 1.9, but let's say we don't know the mass of ammonia which is given. I'll put X. So the mass of ammonia given, first we are going to say number of moles of ammonia divided by the coefficient, which is 4, supposed to be equal to the number of moles of oxygen divided by the coefficient, which is 5. The number of moles is given by mass over molar mass, but we have got a 4, so that will be 4 molar mass. This is for ammonia. So it's going to be equal to the mass divided by 5 molar mass. This is going to be for oxygen. So the mass for ammonia, let's say we don't know, so I'm going to put X there since that's what we want to find, divided by 4 the molar mass for ammonia. So let's start with nitrogen itself, the molar mass from the periodic table. Nitrogen is 14.00674, and then we have got 3 hydrogens, 3 times the molar mass of hydrogen is 1.00794. So the molar mass of ammonia that I'm finding is 17.03056. And this is supposed to be equal to the mass now of oxygen given, that is 4.96 over 5 multiplied by the molar mass of oxygen. Now this is oxygen molecule. So that is going to be, we have got two auctions, but the molar mass of each auction is 15.9994, and that is going to give us 31.9988. So if I want to remain with x, I'm going to say x is going to be equal to, I'm going to multiply this value by the value on top. That is going to be 4.96 multiplied by 4 multiplied by 17.03056, and then divided by this value which was supposed to multiply with x. I'm going to divide by it. So that is divided by 5 multiplied by 31.9988. So let's see what we get to find. 4.96 multiplied by 4 multiplied by 17.03056 divided by 5 times 31.99. So x is giving me 2.11868635 grams. So this is the mass of ammonia that is supposed to react with a given mass of oxygen, 2.11. Now, if this is the mass of ammonia that is supposed to react with a given mass of hydrogen, now consider what you've been given. This is what you expect to use, but you only have 1.9 grams of ammonia. Since what has been given is smaller than what you are supposed to have, meaning that this one which you have been given, when this reaction starts, this is going to complete before oxygen is done, meaning that ammonia is the limiting reagent. So that statement is very important for us to state when you are determining the limiting reagent. So I'm going to say, since the mass of ammonia that is required to react with oxygen is less than the mass, since the mass of ammonia that is required to react with the mass of oxygen given is more than the mass of ammonia present, ammonia is going to be used up first. Therefore, ammonia is the limiting reagent. So ammonia is the limiting reagent in this compound. Alright, and then the next question, part 2. How many grams of excess reactant remain? How many grams of excess reactant remain? Okay, so I want to find out how many of the excess is going to remain. So how do you get to do that? So for you to be able to determine the value for that one, let me just write the number of moles of, the molar mass of ammonia down here, because it's going to be necessary to be used. 17.03056. Alright, so this is the question that we've been given. Now we want to find the mass of excess reagent which remains. So we know that if ammonia is the limiting reagent, definitely oxygen is going to be the excess reagent. Since this one is in excess, so what are we going to do? Well, the one which is in excess, we need to find the mass of oxygen that is supposed to react. So we're going to say we don't know the mass of oxygen that is supposed to react. So we know that this is going to be mass divided by 4 molar mass of ammonia. This is going to be mass of oxygen divided by 5 molar mass of oxygen. So now we are going to use the mass of ammonia that is present, that is 1.90, divided by 4 the molar mass of ammonia, that is 17.03056. This is supposed to be equal to, we need to find out the mass of oxygen that is supposed to react. So I'm going to say 5 over, mass over 5, the molar mass of oxygen. We have got 2 molecules of oxygen, 2, and each oxygen has got a molar mass of 15.9994. So what I want to find is M, that is the mass of oxygen that is going to react. So mass is going to be, I'm going to multiply these two values, that is a 1.90 multiplied by 5 multiplied by 2 multiplied by 15.9994, and then divided by the value which you're supposed to multiply the m, which is this one in the denominator. I'm going to divide by it. So divided by 4 multiplied by 17.03056. Alright, so let's go on and get to punch this. So 1.90 multiplied by 5 multiplied by 2 multiplied by 15.9994 divided by 4 multiplied by 17.03056. So this is given me 4.462 grams of oxygen. And this again just confirms that oxygen is the excess reagent, because this is the only mass that is required to react with ammonia which is present, but we've been given 4.96, which is more than the mass required. So meaning that it is in excess. So to find the mass which is in excess, it is the mass which is available, which is the 4.96, minus the mass that is expected to be used, which is 4.462. So 4.96 minus what is expected to be used. So the mass in excess is 0.4976 grams of oxygen. So this is the excess. How many grams of nitrogen is formed? How many grams of nitrogen monoxide is going to be formed? So determine the number of moles or the grams of the product formed. You always use the limiting reagent. Always use the limiting reagent. So I'm not going to be interested in using this value. So I'm going to say the mass of the limiting reagent, which is ammonia, divided by, we've got 4 molar mass of ammonia. That is going to be equal to the mass divided by 4, the molar mass of nitrogen monoxide. Now this is the 4, this is the 4. So definitely this one and this one, they're in a more ratio of 1 to 1. So those values are going to, the 4s will cancel out. So I'm going to say the mass of ammonia given, that is 1.90, divided by molar mass 17.03056. This is going to be equal to the mass of nitrogen monoxide to be formed divided by the molar mass. So the molar mass, we have got nitrogen monoxide. First, nitrogen is 17. Nitrogen is 14.00674. And then oxygen is 15.9994. So the molar mass is 30.00614. So to remain with the mass, we get to multiply these two values, that is 1.90 times 30.00614, and then divide the value you're supposed to multiply with m, which is 17.03056. 1.90 multiplied by 30.0, then divide that by 17.03056. So this is going to give us 3.3476 grams of nitrogen monoxide. The isotopic mass of 17, this is chlorine. Alright, that is an atom of chlorine written as 17 chlorine, like that. And then we also have 17 chlorine with a 37 here. So you can see they all have the same proton number, but the mass numbers are different. So the isotopic mass are, for the first one given, this is the isotopic mass, because we have been told respectively, so in that order. So the first one given, that is 34.968852, and then the next one given is 36.965902 atomic mass units. So this is atomic mass units. Now the atomic mass of chlorine, that is the relative atomic mass of chlorine, is also given. So what would be the isotopic percentage composition of the two isotopes? So the percentage composition of the two isotopes, if I get the percentage composition of this one, I add to the percentage composition of this one, I'm supposed to get 100%. And 100% as a decimal is 1. So if I say the percentage composition of this one is x, then this one is supposed to be 1 minus x. If I add x and 1 minus x, I'm supposed to get 1, which is 100%. And we know that relative atomic mass is given by mass 1 multiplied by its abundance plus mass 2 multiplied by its abundance, like that. So if we add another one, we continue to add. Relative atomic mass is given as 35.453. That will be equal to mass 1, that is 34.968852. The abundance is x, plus mass 2, that is 36.965902. The abundance is 1 minus x. From here, this is going to be 35.453. That is equal to 34.968852x. Then plus, I'm going to multiply this by what is inside the bracket. So that is going to be 36.965902 minus 36.965902x. So get to put like terms together, this one minus this one, because they all contain x, which is 34.968852 minus 36.965902. So that is going to give us negative 1.99705x. Then I'm going to get this value and take it the other side of the equation, so it's going to become negative. And on the other side of the equation, I've got 35.453. So it will be minus the other term which is going the other side, and that is 36.965902. And that is given me negative 1.512902. So to remain with x, divide both sides by this value. Therefore, x is going to be this number, which is a negative 1.512902 divided by negative 1.99. Okay, that is 1.99. So the value which is here, my PC cannot see that value well. So let's say whatsoever is here, since I didn't write it well myself. So let's say that is 99705. And then that is going to give us 0.757. So this is the molar mass. This value which is here, I've got a fault on my PC, I can't see it well. So if this is a 7, then this value is correct. But if it is not, we should be able to use the right value which is there. So what I'm finding is x is that value. So meaning that the abundance for this chlorine, we can now write the final answer. The abundance of 17 chlorine with a mass of 35 is going to be 0.75, because that is x. Now this is a decimal. As a percentage, multiply this one by 100. So this same value here as a percentage is 75.76%. And then the other one, which is 17 chlorine with a 37, the percentage then is going to be 1 minus x. Now x, we've already found this percentage, and this one as a percentage is 100. This is going to be 100 minus 75.76. That is going to be 17. Let me just do that again. 100 minus 75.76. That is going to be 24.24%. So these are the percentage composition, and it is important for us to write this at the end, because if we don't, the marker might not know which percentage composition is for which compound. And the very last question in this drill sheet: calculate percentage yield of a reaction in which 41.5 grams of tungsten 6 oxide reacts with excess hydrogen to produce metallic tungsten and 9.5 grams of water. So what we have is tungsten 6 oxide, which is reacting with excess hydrogen, and we are producing metallic tungsten and water. So this is going to be a solid. We know this is a liquid, this is a gas, whatsoever state this one is. So we need to balance this reaction. So we can see two hydrogens, but we have got three oxygens, we only have one oxygen here. So to balance the oxygens, I'm going to put a 3 here. And then I've got 6 hydrogens, so I'm going to put also a 3 here. Right. So now the reaction is balanced. 1 tungsten, 1 also here. So since this one is in excess, meaning that the one which is limiting is this one, and that's the one that you use to form product. So from what you've been given, we have 41.5 grams tungsten oxide. So this one, the mass given is 41.5 grams, which is reacted. Now we've been given that water which is formed is 9.50 milliliters. So the water which has been produced is 9.50 mils, and this is the actual yield. Now we want to calculate also the theoretical yield. For us to be able to calculate the percentage yield of a reaction, you get to look at the product. The mass of the product given is the volume of the product given is of water. So I mean that I'm supposed to also calculate the theoretical yield of water, and then I can be able to determine what the percentage yield is going to be. So mass divided by the molar mass of tungsten 6 oxide is going to be equal to mass divided by molar mass of water. Now because we have got a 3 in front of water, I'm going to put a 3 down here. So this is going to be mass of tungsten 6 oxide given is 41.5 divided by the molar mass. So we get to check on our periodic tables. Tungsten itself, the molar mass is 183.84. And then plus we have got 3 oxygens, and each oxygen is 19. Sorry, each oxygen is 15.99. 9994. So this is going to give us 231.8382, and this is going to be equal to the mass of water. Now that is what we want to find. That is the theoretical yield divided by 3, the molar mass of water. We know that in water I've got 2 hydrogens with a mass of 1.00794, and then plus oxygen with a mass of 15.9994. Right. So let's do that. So we're going to say 2 multiplied by 1.00794, and then plus 15.9994. So this inside has given me 118.01528. Then I'll multiply by a 3, which is this 3 which is here. Okay, the answer that I get, I also multiply with this one which is on top. So I'm finding that mass is going to be, if I multiply this by this, that is giving me 2242.90236, then divided by this value which was supposed to multiply with this one. So that is going to be in the denominator, that is 231.8382. So the mass of water that has been produced divided by 231.8382, that is going to be 9.6744 grams of water. Now for the water that the mass of the product, the actual yield of water given is in terms of volume. We also know that mass is equal to density times volume. So the density given is 1 gram per milliliter times the mass given, that is 9.50 milliliters. So this will cancel with this. So meaning that the mass of water produces 9.50 grams of water. So percentage yield is given by the actual yield over theoretical yield multiplied by 100%. All right. Now, from what we are supposed to have is the theoretical yield is always greater than the actual, because for you to have the actual yield, like there are always some losses. That is why the actual yield is always smaller than the theoretical. So you don't find the actual being greater than the theoretical because of losses in the reaction. So the actual is 9.50 grams. The theoretical is 9.674 grams. Then multiply that by 100%. That is 9.5 divided by 9.67 times 100%. This is going to give us about 98.2 percentage as the percentage yield of the reaction. Well, thank you so much for watching this tutorial. Hope it was helpful and stay blessed.